This is a training module on the JenNet wireless microcontroller JN5139. Welcome to the training module on the JN5139. This training module introduces the wireless connectivity solution suitable for IEEE 802.15.4 and ZigBee applications. This controller has a 32-bit RISC processor with wireless transceiver. The JN5139-XX-MYY family is a range of surface mount modules that enables users to implement systems using IEEE 802.15.4 and ZigBee with minimum time to market and at the lowest cost. The modules use JenNet's JN5139 wireless microcontroller to provide a comprehensive solution with high radio performance and all RF components included. The CPU of the JN5139 is a 32-bit load and store RISC processor, which includes the radio system, a 32-bit RISC CPU, ROM and RAM memory, and a range of analog and digital peripherals. SPI configuration allows the flash memory device to be programmed using an external SPI programmer if required. The memory can be programmed over the UART by using the flash programmer software provided by JenNet. The instruction set manipulates 8, 16, and 32-bit data stored in big endian format. The JN5139 is a low-power, low-cost wireless microcontroller suitable for IEEE 802.15.4, JenNet, and ZigBee applications. The CPU of the JN5139 is a 32-bit load and store RISC processor. It has low power consumption suitable for battery-powered applications and has the high performance to implement a wireless protocol at the same time as complex applications. It has efficient coding of high-level languages such as C provided with the JenNet Software Developers Kit. It features a linear 32-bit logical address space with unified memory architecture, accessing both code and data in the same address space. The CPU contains a block of 32-bit general-purpose registers. JenNet is a network protocol stack designed to work with JenNet's family of modules and wireless microcontrollers that integrates a 32-bit microcontroller, peripherals, and a 2.4 GHz IEEE 802.15.4 compliant radio. Two standard ROM configurations are available that integrate IEEE 802.15.4b and ZigBee protocol stacks. The JN5139-001 integrates IEEE 802.15.4b for development of proprietary systems, and the JN5139-Z01 integrates the ZigBee protocol stack. This supports the coordinator, router, and end device configurations. Custom ROM masks will support the integration of user code into ROM, attractive to higher volume applications. Hardware interrupts generated from the transceiver, analog or digital peripherals, and DIO pins are individually masked using the Programmable Interrupt Controller, PIC. Interrupts are used to wake the JN5139 from sleep. The peripherals, baseband controller, security code processor, and PIC are powered down during sleep. DIO interrupts and optionally the wake-up timers and analog comparator interrupts remain powered to bring the JN5139 out of sleep. The wireless transceiver comprises a 2.45 GHz radio and OQPSK modem, a baseband processor, a security code processor, and PHY controller. These blocks, with protocol software provided as a library, implement an IEEE 802.15.4 standards-based wireless transceiver that transmits and receives data over the air in the unlicensed 2.4 GHz band. The modem performs all the necessary modulation and spreading functions required for digital transmission and reception of data at 250K bits per second in the 2.45 GHz radio frequency band in compliance with the IEEE 802.15.4 standard. The transmitter receives symbols from the baseband processor and uses the spreading function to map each unique 4-bit symbol to a 32-chip pseudo-random noise sequence. Offset QPSK modulation and half-sign pulse shaping is applied to the resultant spreading sequence to produce two independent quadrature phase signals I and Q, which are subsequently converted to analog voltages in the radio transmit path. The baseband processor provides all time critical functions of the IEEE 802.15.4 MAC layer. Dedicated hardware guarantees air interface timing is precise. The MAC layer hardware-software partitioning enables software to implement the sequencing of events required by the protocol and to schedule timed events with millisecond resolution, and the hardware to implement specific events with microsecond timing resolution. During reception, the radio is set to receive on a particular channel. On receipt of data from the modem, the frame is directed into the TX/RX frame buffer, where both header and frame data can be read by the protocol software. The Serial Peripheral Interface, SPI, allows high-speed synchronous data transfer between the JN5139 and peripheral devices. The JN5139 operates as a master on the SPI bus, and all other devices connected to the SPI are expected to be slave devices under the control of the JN5139 CPU. The SPI bus employs a simple shift register data transfer scheme. There are three dedicated pins: SPIC clock, SPI-MOSI, SPI-ISO, that are shared across all devices on the bus. The JN5139 provides 5 slave selects: SPI select 0 to SPI select 4 to allow 5 SPI peripherals on the bus. The Intelligent Peripheral IP interface is provided for systems that are more complex, where there is a processor that requires a wireless peripheral. As an example, the JN5139 may provide a complete JenNet wireless network interface to a phone, computer, PDA, set-top box, or a games console. The wireless peripheral may be controlled via one of the UARTs, but the IP interface is intended to provide a high-speed, low process overhead interface. The IP interface cannot be used with the CPU in the DOS mode. Transfers are started by the remote processor assuming the IP_select line and terminated by the remote processor deasserting IP_select. The remote processor, acting as the master, must determine the larger of its incoming or outgoing data transfers and deassert IP_select when all of the transmit and receive data has been transferred. Two general-purpose timer counter units are available that can be independently configured to operate in one of 5 modes. The clock source for the timer unit is fed from the 16 MHz system clock. This clock passes to a 16-bit prescaler, where a value of 0 leaves the clock unmodified and other values divided by 2 prescale. The counter is optionally gated by a signal on the clock gate input, TIM CK_GT. If the gate function is selected, the counter is frozen when the clock gate input is high. An interrupt can be generated with the counter when the counter is equal to the value in either of the high or low registers. The internal output enable signal enables or disables the timer output. The JN5139 has two independent universal asynchronous receive transmitters, UART, serial communication interfaces. These provide similar operating features to the industry standard 16550A device operating in the first-in, first-out mode. Each interface performs serial to parallel conversion on incoming serial data and parallel to serial conversion on outgoing data from the CPU to external devices. This means that the CPU is freed from handling data on a character-by-character basis with the associated high processor overhead. The JN5139 includes an industry-standard two-wire synchronous serial interface (SIF) that provides a simple and efficient method of data exchange between devices. The system operates as a master-only and uses a serial data line SIF_D and a serial clock line SIF_clock to perform bidirectional data transfers. A configurable prescale register allows the interface to be configured to operate up to 400 kbits per second. The clock generator handles the clock stretching required by some slave devices. The clock and data lines SIF_D and SIF_clock are alternative functions of DIO lines 15 and 14 respectively. The serial interface function of these pins is selected when the interface is enabled. They are both bidirectional lines connected internally to the positive supply voltage via weak 45 k ohm programmable pull-up resistors. The JN5139 contains a number of analog peripherals allowing the direct connection of a wide range of external sensors, switches, and actuators. A common reference VREF for the ADC and DAC can be selected between an internal band gap reference or an external voltage reference supplied by the VREF pin. Gain settings for the ADC and DAC are independent of each other. The ADC and DAC are clocked from a common clock source derived from the 16 MHz clock. The digital to analog converter DAC provides two output channels and is capable of producing voltages of 0 to VREF or 0 to 2 volt ref, where VREF is selected between the internal reference and the VREF pin, with a resolution of 11 bits and a minimum conversion time of 10 microseconds, 2 MHz clock. The JN5139 device requires a minimum of external components to support wireless applications. A crystal, some decoupling components, and printed antenna are all that is required for the lowest cost bill of materials and smallest size. An external bootloader flash may be used for optional program code storage.